In this system, gas flows up through a production riser. In addition to the gas, some condensate can be present in this line. Most of the time, only gas exits the riser and enters the system. Every 5 hours, however, a slug forms and travels up. The slug has a high velocity of 12.5 meters per second and a length of 4 meters. This gives a slug duration of 0.3 seconds. In the quasi-static analysis, however, the slug duration is not relevant. Note that with a slug length of 4 meters, in some cases 2 elbows will be influenced at the same time. This is not considered in the current case study, but may be relevant for real-life applications. The pipe is standard schedule 8-inch pipe made of steel. The system has multiple bends and valves and ends in a large header. In the header, the flow velocities reduce drastically and the slug disappears. With a slug velocity of 12.5 meters per second, a slug density of 900 kilograms per cubic meter, this results in a force of about 4.5 kN for a 90-degree elbow. At 45-degree elbows, the force is about 3,200 Newton. This is in both directions and without the dynamic load factor. With a DLF of 2, the force at the 90-degree elbow is 9 kilonewtons. Let's have a look at what that does in a very sporadically supported system. To each of the elbows, we apply 2 loads. So for example, for this pipe running in x direction, we want to apply the force in minus x, as the slug is stopped in that direction. In addition, we will also apply a force in minus z direction. This because the slug has to start moving in the plus z direction, and therefore pushes on the pipe in the negative z direction. In this case, the DLF is added through the load cases. It could, however, also be included in the force magnitude applied per elbow. We go through the whole system like this, while making sure that nearby elbows get a force in different force vectors, ensuring they do not cancel each other out. At the 45-degree elbows, the same is done, but then with a lower force. The slug travels from the start of the system all the way to the large header. All of the changes in direction it encounters on the way get the force applied. Important for the slug analysis is also how to define the load cases. These may be governed by a pipe stress specification, but otherwise you will have to create them yourself. In this case, we will use the B31.3 code to perform the stress analysis on the system. In that code, it states that the stresses due to occasional loads may be calculated using the equations for stress due to sustained loads. The sum of the stress due to the sustained loads and the stress due to the occasional loads shall not exceed 1.33 times the basic allowable stress. One option would therefore be to combine the slug forces with the sustained conditions in Caesar 2. In many cases, this will result in quite realistic results, but it is not entirely correct. In reality, the slugs will pass during operation, which means that the system is hot. Supports may therefore lift off, which can change the behavior of the system when a slug passes. Also, the loads that the supports have to be able to withstand are based on a combination of slug loads as well as operating loads. More realistic is therefore to add the forces to the operating conditions, as is shown in this overview. One force is added per load case. Then, the effect of the slug is isolated. This effect of the slug can then be added to the sustained case to obtain the load case with the occasional loads plus sustained loads as required for the B31.3 stress check. Note that it is also important to design the supporting such that it can withstand the dynamic slug loads. For this, use the operating cases, as the forces exerted by the thermal expansion are felt along with the slug forces. If we run the analysis the way it was set up, there is an overstress in our sustained plus slug case in one location. We see that the system is quite light on its supporting and that the displacements caused by the slug are rather large. The location of the highest stress is at a T, which makes sense because the sieve on the T will increase the stress locally. Just adding some supports in the vicinity of this T will reduce the stress and lead to the system passing the stress check. Normally, you would also check the flanges, but that's outside the scope of today's case. Even with the additional supports in place, we can see that the displacements due to the slugs are rather large. This might be an incentive to add more supporting than only the ones required due to the stress in the system. Another incentive to add more supports than indicated by the quasi-static stress analysis can come from the dynamic analysis.